This video we're going to talk about what are called equipotentials. And basically these are lines where as long as you move along them you stay at one potential or one potential energy. And so let's take a look at this. Let's say we had an electric field. Just hopefully make a better line than that. Intended that to be nice and straight. So we have an electric field that's like this, a nice uniform electric field, and we can move around in it. And if we move perpendicular to the field, if we move in this direction, like along this line, then if you look at the equation for this, voltage in an electric field is negative ED, and this is derived from the potential energy one, or we derived it from the potential energy one, which is negative QED, and we derived this from the work equation, which is force parallel to displacement, which means this QE has to be parallel to D, but Q has no direction, so it's E parallel to D, which means here it's also E parallel to D, which means that only any movement parallel to D is actually going to change our potential energy or change our voltage. So moving perpendicular to E stays at a constant voltage. And so that means that we can draw these lines where everywhere they cross an electric field they are perpendicular to it. And these lines are called equipotential lines. Okay? And so as long as you move along that line, you stay at one voltage. So we could say, this is V1, this is V2, this would be V3, and you stay here, you stay at V1, and the only time work is done is moving between these equipotentials. Now, technically there's an infinite number of equipotentials because there's V1 and then there's plus an infinitesimal little amount would be a next voltage right next to it, but we don't want to draw all of them. But moving between these lines of equipotential, that's where work is done. That's where you change voltage, but staying on them, no work is done. And so you can draw them for all kinds of different situations. So we could say we have a positive charge here, and the field lines go out radially like this, right? And if you were to draw these lines of equipotential, you want to stay perpendicular to it at every point, and so the way these are typically drawn is you draw them with these dotted lines. So make sure if you're ever going to draw them on a test, this was supposed to be a much better circle than it turned out to be. But everywhere it crosses these field lines, it stays perpendicular to them. So that would be one equipotential, and this would be another one out wider. So the uniform electric field equipotentials are fine. They're just parallel lines perpendicular. The single charge like this, the equipotentials are easy. They're just circles, concentric circles around it. And you could go around this, basically orbit that charge, and it takes no work to orbit it, and that's fine. What about something like a positive and a negative charge next to each other? So let's say we had a positive charge and a negative charge here. Well, we know that the field lines look something like this, where they curve over at each other, right? They do something like this and curve over, and they curve in and like this. They do something like this. They curve in. I think I'm drawing those curves backwards. Sorry. They curve this way. That's a little better. And I'm sorry, my picture's pretty messy. And they curve like that. And so how would the equipotentials here look? Well, you got to go and you can kind of see them and kind of draw them out again by staying perpendicular. But basically what happens is you get something like this. So in between we got to stay perpendicular, and then we have to turn and turn a little bit. And so the close-up one is close to being circular because it's closer to that negative charge. But you move out a little bit and you got to stay perpendicular, and you have to stay perpendicular. So you have to go out here and you'll stay perpendicular, and it'll kind of go out further on that side, going perpendicular, 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 perpendicular. And then the same thing here. You go out, stay perpendicular, perpendicular, and then you end up coming way out, it gets further out. And so you stay on these perpendicular lines as you go kind of far out, and it gets out here like this. And then the same thing on this other side, you know, you draw one here, it'd be almost circular, and then here it comes and stretches further out, and then here it stretches out a little further, and so on and so forth. And so it's something like this, where you get these lines of these equipotential lines, and this, you know, is going to get way out here like that. I'm getting just wasting a lot of time drawing these, and so this is going to go, you know, way out here. It's going to spread out further and further and further. And so your equipotential lines, it looks something like that. They're a little more symmetric than I drew them, but you know, it's the best I can do here on this thing. And so what you notice is that these equipotential lines, they're closer together in here, and they're further apart out here. And so it's kind of like the electric field lines. The closer the electric field lines are, the stronger that electric field is. So if you were moving, say this, you were going to move some distance d, and let's just say this distance we had is this long, right? Well, if I move that far right here, right, I'm only really crossing one equipotential line, and I'm not going to have a big change in potential, not a big change in voltage or potential energy. And so it's a lot easier to move this distance out here than, let's say, if I did that same distance in here. If I came in here and I did that same distance. Now, if you look at this, I'm crossing multiple equipotentials here, and I'm crossing them a lot faster. So there's a bigger potential energy difference moving in here than there is out here, which means it requires more work to move around in here than it does out here, which also makes sense because if you look at our field is a lot stronger in between the charges than it is out here, and so you'll have a bigger change in potential energy moving through that stronger field. Okay, and so the way that I really think about these equipotentials is I think about a topographical map. So you've seen this. So you'd look at something, and you know, you've got some map like this, and this will be 100 feet, and then you know, it'll do something like this. You know, it's just, and this will be 90 feet, and this could be, and then it comes over here, and it, you know, it does something like this, and this is, you know, 80 feet, and this one over here, it comes and it, you look at it, and it just does something like this, and you've seen this kind of thing when they show a picture, or hopefully you've seen this kind of thing when they show a picture of like a mountain or something like that. It's a topographical map, so you can look at this and you can see just by looking at this, it's this two-dimensional map, but they put in these lines, and these lines are of equal heights instead of equipotentials. And you can look at it and say, well, look, if I go right here, if I move just a little bit right here, I'm at 100 feet, and I move this distance, I'm down to 70 feet. But if I'm over here and I move that same distance, I'm at 100 feet and I'm at like 92 feet or something like that. I'm not down to 70 feet like I would be here. So you would be able to say that it's a lot steeper over on this side than it is on this side. That this little area in here is where it is steepest, right? So you'd be able to see that. And so if we went through and we wanted to think about, well, then if you think about these equipotentials as a topographical map telling you how steep it is, well, right here is where it is steepest, right? It's going from like a high down to a low in a real steep, fast turn, and then this is a gentle slope out here. And then how do the electric fields fit into that? Well, as I've told you, I think you should think of electric fields as flowing water. So you could imagine if we had rain falling on this, right? And I'm gonna, you know, if rain fell down on this, most of the rain, and we mapped out like a field, like the speed of the rain. Well, the rainwater is gonna wash down this way the fastest. So we'd have a lot of arrows there about it being faster there, and then it's gonna go a little slower out this way. And then out here, it's going down a gentle slope, so it's going real slow. And these would just kind of spread out as the water went down. And if I wanted to represent how fast that water was flowing down, I would do something like this, right? This is how the water would go down the mountain. It's going to go slowly over here, so my lines are going to be far apart. It's going to be really fast over here where it's flowing down the hill, where it's real steep, so I'm going to have a lot more lines. It's going to be closer together. And it's kind of like this, right? Where these lines are closest together happens where it's steepest, and that's where you end up with the fastest flowing water or the strongest electric field, okay? So this kind of idea of voltages are like a topographical map, and then these electric field lines flow around in them like flowing water would across a topographical map like that. I think it's a good way to kind of think of these equipotential lines, okay? then all you have to really remember is just to pay attention to what voltage you're moving between, what change in voltage it would be, and you'd be able to figure out then how much work was done based on that. Because if you remember, our change in potential energy, of course, equals work, and you can figure that out if you move to charge through there. Okay? I think that's pretty much everything. Spend some time kind of thinking about this correlation to a topographical map, and hopefully this will kind of make sense to you, and you can look up some more examples of how to draw these and everything. Okay? Just, main point, really remember, as long as you're moving along one of these lines, it takes no work. So if I move along this one, even though it's not a circular path, I'm not doing any work. I'm just moving along this equipotential here, okay? I think that's it.